Okay, good afternoon, everyone. So good to see that you are sticking with the chaos, and hopefully we will get quantized today. We'll see. So we will talk first about the ingredients and the definition of classical chaos. The first ingredient is what is sometimes called transitivity, sometimes ergodicity, and sometimes the existence of a dense orbit. So all of them more or less synonyms. So in English, what it means is that you have some phase space on which you have this dynamics which you're considering. You will call this dynamics transitive if almost all initial conditions come arbitrarily close to any other point in the allowed part of the phase space. For example, if you have an energy shell and energy is conserved, then a point of every initial, almost all initial points in that will visit every other phase space in which the energy is compatible with that energy. So in terms of a more formal definition, so if you have some mapping, it could be a flow or it could be a discrete map, doesn't matter. Omega is your phase space, and there is this mapping or a flow from omega to omega. Then consider two sets, U and V, such that they don't intersect, two separate sets. Then they will, and then evolve one of those sets, let's say U, evolve this or integrate this under some flow, so you get Fn of U after a time n. Then this mapping F will be transitive if F to the n U intersects with V at some point. It's not a null set. Okay. So that means that almost every set intersects every other set. So it's going all over the place. So that's what we think of as ergodicity. When we study ergodicity, we say that it's visiting every part of phase space. So let's see. So here I have this doubling map 2x modulo 1, which I did last time. And I have just started from one point, and this is the phase space for us, which is 0, 1. And every time there is a point, you can see that it's being mapped onto that. So you can see that it is ergodic on 0, 1 most likely, and it is in fact ergodic on 0, 1. It visits almost every other point arbitrarily closely. If you wait, it will be actually uniformly distributed on this. Okay, so we're just starting with one point, and then as time goes by, this point is visiting every other neighborhood of every other point. So that is what is the first ingredient of chaos. So chaotic system should be ergodic. The next ingredient of chaos may seem a little bit contradictory, in the sense that we are going to say that there are a lot of periodic orbits. Okay, so there is a dense but measure zero set of periodic orbits. Arbitrarily, what does dense mean? Dense means that, again, arbitrarily close to any point on the phase space, omega, is a periodic orbit. That means that the closure in the set of sense theory, that means the limit points, if you can include the limit points of every sequence of periodic orbits, that is the entire phase space. So the closure of the set of periodic orbits is the phase space. So is this clear? So we have a phase space omega, arbitrarily close. You just pick some point randomly, arbitrarily close to that, arbitrarily, up to you. You will find a periodic orbit. So they are dense everywhere. So for example, coming back to our solvable model of this doubling map, we said that the dynamics on this is simply a left shift, right? You express this initial condition as in binary and then do a left shift. So where are the periodic orbits? Well, you take an x0 of this form where a0 to al minus 1 are L bits, and just repeat those L bits infinitely often, right? That's what the bar means. Then these are all period L points, because clearly if you shift this to L times, if you have shifted this out, you come back to this initial condition. Okay, so for instance, if you take a sequence of length 2, so like let's say 0 1, 0 1 bar gets shifted to 1 0 bar, and then next it's back to 0 1 bar. So that's a periodic orbit of period 2. And in decimal, it's 1/3 going to 2/3 back to 1/3. So that's a periodic orbit of period 2, and we'll call 1/3 a period 2 point. So 2 periodic points make up the orbit in this case. So if you take period 3, for instance, so you have this string of, let's say, 0 1 1, it will get shifted like this 3 times and come back to itself. In decimal, it's 3 by 7 going to 6 by 7, that is just twice of that. And here it will be twice of this modulo 1, that's 12 by 7, modulo 1 is 5 by 7. Twice that is 10 by 7, modulo 1 is 3 by 7, it's back. So you see, periodic orbits are there, easy to find. So in fact, for period of length L, there are exactly 2 to the power of L periodic points of period L, because you can have 2 power L possible strings of length L. So there is an exponentially large number of periodic orbit with the period L. Roughly speaking, since every periodic point is on a periodic orbit, and periodic orbits are of length L, roughly speaking, the number of periodic orbits is 2 to the power of L divided by L. This many number of periodic orbits of period L. You can find the exact number. It's an interesting mathematics problem. I'll leave it to you. If you're interested, you can find out what is the exact number. But the point is actually, if you look at the number of periodic orbits of period L, let's say n of L, for large L, it is going to scale as exponential of something times the period divided by the period itself. And this quantity here is another number, like we have already encountered Lyapunov exponent from the sensitive dependence on initial conditions. This is another number which characterizes chaos. It is called the topological entropy. So this is a topological entropy of the system. For the doubling map, it's a very simple map. Therefore, all these numbers coincide. It is log 2 for the topological entropy is also log 2 for the doubling map. And in fact, it's also the logistic map at r equal to 4 topological entropy. The number of periodic orbits is 2 power L for the logistic map, also at r equal to 4. It's called topological as opposed to other things because you can make a transformation of this function to some other function using some smooth map. You can conjugate it with some other function, and that will be this number of periodic points is actually some number. It is independent of the metric metric that you're using to measure distances, whereas Lyapunov exponent depends on what metric you're using. So in a sense, that is not a topological measure. And therefore, in general, this topological entropy is larger than or equal to the Lyapunov exponent. Okay, so in a chaotic system, there are this dense set of periodic point orbits, but they are all unstable, of course. Otherwise, you will have, if they are stable, around that you will have regions which are trapped and it will not be transitive. Okay, so there are this infinity of dense set of periodic orbits, but in fact they're all unstable. So in fact, the periodic orbit set is again like a set of rational numbers. Rational numbers on the unit interval forms a dense set. Arbitrarily close to any number, you can find a rational number. It's also measure 0. The probability of finding a rational number is 0. While non-periodic orbits are like irrational numbers, they are of measure 1. Yeah. Yeah. Dense. They have to be dense. They are dense. They are not at different energies, same energy. Same energy, you will have an infinite number of periodic orbits of a given period. So this length is L. So you have to ask what is the scaling of the number of orbits as a function of the period. And as a function of period, for the same energy, it will be growing exponentially. And it does for the billiards also. Yeah. 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 Yes, I mean uh, a dense but measure zero. So what? So this is the best way of understanding this is this. So by dense, one means that okay, suppose we have this set of periodic points. Like let's just take even this doubling map on this unit interval 0, 1. Now you take any point in this, the statement is that arbitrarily close to that you will find a periodic point. So you will call some set dense if there is such a property. Measure zero means that if you find a Lebesgue measure or you try to find out the mass on this, it will be zero. Just as the rational numbers are of set measure zero and they are dense. So maybe I can explain a bit of that. Try to explain that, a bit of that on the board. First of all, the fact that given any point in this interval 0, 1, any point, we just randomly pick this point arbitrarily close to that. That means that you have fixed this and then somebody has given you an epsilon which is something very small, 10 power minus or 2 power minus 20. That's a part in a million that we were talking about. So you're given some interval around here, epsilon interval, there will be a periodic point there. So is that clear? All you need to do is to find a thing like that. So suppose you have a number here, right? That is some, there is some binary expansion of that, A0, A1, etc. So now in order to find a periodic point there, to within this accuracy, all you need to do is truncate it maybe after the 20th, maybe 23 or something like that, doesn't matter, right? And then repeat it. So the number x was going on and on with some other things, but we don't bother about that. We take till 23, truncate it, and then repeat it. So this will be having a period of 24, and we have, it is now satisfying the condition that it is within epsilon of that point. Is that clear? So obviously, smaller the epsilon is, the larger, highly likely that the period is larger and larger that you're finding. Okay, you just take some point and say, I want within 10 to the minus 100 a periodic point there, you will find it will be a large period, periodic orbit. So that is what dense means, but in terms of measure theoretic sense, I mean, you have some sequence, and that sequence will have some limit point. That limit point, the collection of all those limit points and this set should be the whole phase space. Now the other thing about measure, this is going back to how do you know that the measure of, let's say, like for instance in this case, right, all periodic points are rational numbers. Not all rational numbers are periodic points, they will tend towards periodic points. But let's say that you take even all rational numbers, the rational numbers from a measure 0, you can kind of, because you can arrange rational numbers, they are countable. So you can always count rational numbers like so. So 3, 1, 3, 2, right? So 4, 1. You can include 2 by 4, but since it's already included, maybe I won't. So now you see 5 by 1. This is a standard construction. 5, 3, etc. So it's in this enumeration of all rational numbers between 0 and 1, or they will come somewhere. Some rational number will come, because what I'm doing, I'm fixing the denominator and I'm increasing the numerator from 1 to that number. Okay, so any number, any rational number will appear somewhere in this enumerated list. So now you can, to show that this set is of measure 0, you can take this number and put one epsilon interval around it. You can take this number, put an epsilon square interval around it, and so on. Epsilon cube interval around it. So now the total interval, what is the total length of rational numbers? That's the question here. So then the total length of rational numbers is smaller than this infinite series. You can take out epsilon, geometric series, epsilon by 1 minus epsilon. So as epsilon goes to 0, this goes to 0. So you can cover the set of rational numbers with a length of 0. So that's why we call it a measure 0 set. Periodic orbits are like that. It's a set which is everywhere almost, but set of measure 0. Sorry? Ingredients, yeah. Yeah. No, I did not define ergodic like that. I define it as transitivity. I'll come to that. I have not yet come to that. You can ask that question when we come to that. Okay, yeah. You mean periodic orbits? So, like for instance, suppose there is a non-zero measure of periodic orbits, then there must be a family of them. Like for instance, let's take again just the unit interval. Okay. Now a non-zero measure could be some interval like this. Now if you say that that whole thing is periodic, so then maybe that's going somewhere here, going somewhere here, it's doing something like that. Then there cannot be a separation of the sensitive dependence on initial condition. There cannot also be ergodicity, the first point that we talked about. It's coming back to itself. In a more kind of, a phase spacey language, so we saw those kind of orbits, and then there's chaos and all that. So here, these periodic orbits are of measure 1, or I'm sorry, a non-zero measure, because you have an area of that. Okay, so then there's no chaos there. Yeah. Okay, so let's move on. Yes, yes, you may say that. But I should tell you that a lot of physical theory, both in classical and quantum, is built around periodic orbits. So there is a nice quotation by Predrag Cvitanovic who says that the flesh of chaos is sewn on the skeleton of periodic orbits. So you can do a lot of physics based on these periodic orbits, because you should think also intuitively what's happening. These periodic orbits are dense, they are unstable. So you can actually construct a non-periodic orbit as if it's some segments of periodic orbits. A lot of periodic orbits underlie non-periodic orbit. So periodic orbits can be used in a very concrete sense to find out things like Lyapunov exponents and so on. Like in this case, topological entropy is defined purely in terms of periodic orbits. Yeah. Yeah. Yes. Absolutely. So the third ingredient is the sensitive dependence on initial condition. I won't spend too much time because I've actually illustrated this in some detail. But formally, if you look at a text in dynamical systems, this is how they will define it, not as Lyapunov exponents, But given two phase space points x and y separated by some distance epsilon, then given any delta greater than 0, there exists a time at which the separation is larger than this delta. Okay, so there's no sense of separation being exponential. Basically, it says that some nearby points separate out outside of that. So sometimes this is called Divani's definition of chaos, because it came in his book on Introduction to Dynamical Systems first, that these three ingredients are necessary for chaos. By the way, this is not to do with just maps or one dimension. This is true for anything. That they are transitive, which we will think about as ergodic, dense set of periodic orbits, and sensitive dependence on initial condition. Shortly after Divani's book, there was an interesting paper which proved that if you are transitive and dense set of periodic orbits, then essentially that implies that you have sensitive dependence on initial conditions, especially for maps on compact phase spaces. That means things are not going off to infinity. It's sufficient to be ergodic and have a dense set of periodic orbits. So here is an example of something which is ergodic, but it does not have a dense set of periodic orbits. Is an irrational rotation. We have already encountered this irrational rotation. It comes in all these oscillators with incommensurate frequencies. So theta n plus 1 is theta n plus 2 pi alpha modulo 1. Alpha is irrational. It is transitive because you are rotating it by an irrational angle. So you start from any angle theta 0, it's going to come arbitrarily close to every other angle. But it's clear that there are no periodic orbits at all because it's a rotation. No point is left unrotated. It's not even got a single fixed point or anything like that. Okay. So it has no periodic orbits. Of course, it doesn't have sensitive dependence on initial condition. So let's expand on that. Theta n plus 1. This is an important map because all integrable systems, the angle variable is changing, and the section on the angle variable is like this. So you can immediately solve this. There's a modulo 2 pi. Theta 0 plus 2 pi alpha time n modulo 2 pi. So now delta theta n is just delta theta 0. So that's clear. Nothing is changing at all with time because it's just a rigid rotation. So if I take some initial delta theta 0, the whole thing is being rotated rigidly. Delta theta. So far from not even actually, there is not even a there's not even a exponential. I mean, not even a polynomial drift in these things. It's got no sensitive dependence. Whereas this example here, without the modulo 1, the doubling map 2xn, it has sensitive dependence because it's 2 to the power of n. Anything will if you multiply by 2 and you start with a delta xn, it's going to multiply that delta xn by a factor of 2. So delta x0, so each time. So it's a 2 power n. So it's got a Lyapunov exponent of log 2. However, it is clearly not, it's neither transitive, it's not ergodic, it's not going to go to any point, it's just going to go off to infinity. And how many periodic points it has? Well, only the x equal to 0, it's one fixed point. No other periodic point, it's unstable fixed point. So it's clearly not dense, set, or ergodic. So for all practical purposes, yeah. No, at least mixing should be there. If you want to push it to an equilibrium, I'll come to that. Yeah. Why we are calling this ergodic? Because, if you go back to Boltzmann, right? I mean, that's where the word ergodicity comes from, energy shell. So that's what he envisioned. He said that there is a point on the energy shell. He said it's going to go to every other point on the energy shell. but that's too strong a condition. It goes to almost every other point. So this is sufficient for giving you an equilibrium distribution, but not sufficient to give you a push to equilibrium. Non-equilibrium will not thermalize. I'll show you as we go by. So in fact, this is now, I'm going to define for you the equilibrium measure, okay, equilibrium density. It is in this context just called an invariant measure. So let's do this experiment where we are taking some dynamical system, okay, which is given by this f. K is now the time, okay, x0 is the initial condition, and j is some interval. For example, if we are talking about logistic map or doubling map, we can talk about the interval 0, 1, and we'll just ask, given an x0, what is a fraction of these iterates which lie in this interval j? Okay, so this is this fk, and then this is the time n going off to infinity. So each time it is entering that interval j, we will mark that point and ask what is a fraction of points which are going to visit this set j. So that is what this is. Now you construct a measure or mass. So you say that this is now the mass of the set j. That is the number of points, fraction of points which is visiting it. Then this is an invariant measure in the dynamics. According to the measure, f inverse of j is equal to the measure of j. Okay, if it is, I have put f inverse because these maps that we are considering, they are not monotonic and therefore they don't have an inverse. So there's no unique inverse. So this f inverse of j is the proper definition of this invariant measure. So in general, if suppose you consider like a Hamiltonian system, it doesn't matter whether this is f or f inverse. Okay, so this thing is some measure which is not changing in time. So that non-changing in time can be seen readily from here, because after all we are taking time going to infinity and we are asking what is the fraction of points which is lying there. Okay, so whether we are taking f of that or not, it does not matter. This thing is an invariant measure. And from this we can define an invariant density by saying that that is the derivative of the measure with respect to x, or you can integrate the density over this interval j. That should give you the measure. So that is the mass and that is the density. So for example, for the logistic map at r equal to 4, that is the point at which it's the same, almost the same as the doubling map. If you do this exercise, this is a numerical exercise, you can do this and you will find this histogram of this density, and it will fit this arc sign distribution, 1 over square root of x into 1 minus x. So that means that if you start a distribution already in the interval, which is of this shape, and then if you let the logistic map act on these points which belong to this ensemble, the ensemble will not change. That is like an equilibrium distribution. It's an invariant distribution. So for the doubling map, it turns out that this invariant distribution is simply the uniform distribution. So if a dynamics has an invariant measure mu, this is Birkhoff's ergodic theorem, which says that you can, if phi is any function on phase space, and j is f is the dynamics, j is time, x0 is the initial condition, what you're doing is basically you're observing the orbit, okay, at these times n, and then calculating the average of this function over that orbit. That average is equal to the phase space average, in which this phase space measure is equal to the invariant measure. So this is actually Birkhoff's ergodic theorem. Sujit left, but he was asking about this equality of phase space to time. So this is time average is equal to the phase space average. So you can just think about it in the following way. We already said that things are transitive, which means that if you start from any point, it's going to go arbitrarily close to every other point. And all this measure is saying is that this is a fraction of time it is spending on that interval. So if you are going to measure some function as a function, function on this orbit, then clearly we can forget about the orbit itself and look at how much time it is spending in each of these intervals and weight it by that fraction of time it's spending in that interval. So that is Birkhoff's ergodic theorem. Okay, so the importance of this measure is that it can be used to measure to get these time averages. And you notice that the left-hand side has this x0, whereas the right-hand side does not have this x0. So this is true for almost all x0 again, almost all x0 in terms of the, in terms of again this measure mu, this statement is true. That is, it forgets about the initial condition as you're doing this. Yeah, yeah, exactly. Yeah, yeah. So transitive is same as ergodic. Okay, so here is a... No, it does not ensure chaotic. For example, here is a map which is chaotic. I'm sorry, not chaotic. That is this rotation map. It is ergodic and it has an invariant density which is just uniform on the circle. Clearly, if you have something uniform on the circle and you're rotating it by whatever angle actually, the distribution is not changing. It's kind of obvious. So the invariant density is simply uniform 1 over 2 pi, and that is, you can show that it is ergodic with respect to this invariant density explicitly. I show this because actually you can do this trick for a lot of different things. So in order to show that, take some test function on the circle, okay, phi of theta, expand this in Fourier series. Okay, so there is a constant term plus this series with different momentum. And now let us calculate the left-hand side of Birkhoff's theorem. So sigma of the function of this. So this function is given like this. So we have to put for theta 0 plus, here is what I've written, theta 0 plus 2 pi alpha n. Okay, so that is what I'm doing, theta 0 plus 2 pi alpha n, and then alpha j actually here. And then you can do the sum. Now it's an elementary geometric sum, and then you will get this. Okay, and now as n tends to as infinity, if alpha is irrational, then whatever this k is, some integer, this will not go to 0. And so there's no problem with this denominator blowing up or anything like that. So for all k which is not equal to 0, this will go to 0. And therefore this, as n tends to as infinity, the left-hand side of Birkhoff's theorem will go to A0. That is this constant mode. And therefore the average of this tends to the 0 mode, A0, independent of theta 0. Also the right-hand side of this, Birkhoff's theorem, which is just this, integrate this with respect to theta. Obviously all of them will go to 0 here because of this has got some e to the ik theta where theta k is not 0. And so the only thing that remains is A0. So again you will get A0. So this shows you that in fact this is transitive, it's ergodic with respect to this invariant measure. But of course, it's not chaotic. It doesn't satisfy any of the other conditions. And you can use the same proof to show that the this works for the doubling map as well. So I leave it to you. So the 2 theta n modulo 1. Do the same thing, but now try to prove that the Birkhoff ergodic theorem works for this. And that the invariant density there is also uniform on the interval. Okay, yeah. No, good question. No, it's not. It's not unique, but it is unique if you say that it is, it's absolutely continuous with, so for all practical purposes, it is unique. You can find, I'll come to, in this case, actually, I can't think of any other invariant density, but there are, I'll show you shortly other things where there are many other invariant densities, but they will not be what's it called, continuous or compatible with the Lebesgue measure. So something which is in some sense large and typical. Your number of functions also which are, how useful is that measure? But we'll see that that's actually a problem in classical mechanics, which doesn't appear in quantum. Yes. Quantum people use loosely the word ergodic, although von Neumann defined it. But whenever people are saying ergodic, for example, MBL, they will say that it's ergodic phase. They mean that it's chaotic, but actually, well, yeah, I mean, strictly speaking, no, ergodic does not imply. It's what? Normal. Misnomer. Okay, okay. Okay. No, that's going outside my subject matter. Sit on, sit on. Huh. Universality. There is a lot of universality in quantum chaos, especially in classical. There is, let's say, statistical things, but universality is there in some aspects. For example, we saw in the logistic map, the very famous universality, RG, your favorite topic, was used to uncover that universality. That is how the period doubling bifurcations, the Feigenbaum constant, 1988, that's a classic work. So that's a universal number. You will find it in experiments, in logistic map, you'll find it experiments in turbulence, real experiments. So yeah, there's some amount of universality there. Okay, so now those where the invariant measure is kind of an equilibrium density. Okay, so what about non-equilibrium? If we put in some density which is not an equilibrium density, obviously that's going to change. So let's do that here for the logistic map. I said that arc sign was the equilibrium density or the invariant measure. Now let's take at time 0 a uniform density on this, which it is not. In time 1 itself, you see how it is deformed like this, and at time 2, it's almost looking like the invariant density, and time 3, it's looking even better. So very short time scale, the system has quote unquote equilibrated from a non-equilibrium distribution to the invariant density. And you can describe how this is going using the so-called Perron-Frobenius operator. So here is an operator which is taking you densities to the density. So this is density at time n, okay, that is rho xn, and this is density at time n plus 1. The operator which is connecting this is called the Perron-Frobenius operator. And how is that? Well, this is how it is defined, right? I mean, this is saying that how are you getting the density at time n plus 1? You have the density of points at time n, and this is at y. You're finding out you're mapping y to x. So delta x minus f of y, and then you're integrating out over all y. And that gives you this density at time n plus 1. So basically you're taking all the points in y at time n, and you're evolving it forward by one time, and you're getting the new density at time n plus 1. Okay, so this is the definition of the, so you can yeah phase space points. No, nothing. I mean, look, there will be periodic orbits and so on in this thing, but I'm not bothered about that. Like in this case, I'm just populating, I'm taking a uniform density of points on this, right? But I can take some other density on this, some unit interval. I'm taking, let's say, all points uniformly in some interval. And then I'm asking, where is that thing? So that will spread out to maybe something like this. So each of these points. So there is some density. So in general, there's some density, and then it's becoming something else. We're just doing Liouville equation. Yeah. So now the fact that in these maps that I'm talking about, like this logistic and the doubling map, there are two such for a given, so all y such that f of y is equal to x. So because you want all orbits which are landing in x, x is where you want to find the new density. So there can exist two values of y such that f of y is equal to x in these 2-to-1 maps, like the logistic and so on. But in general, you can have more than 2-to-1. So this is a general sum like this. So this you can evaluate quite easily like this. So this is the density at time y divided by the derivative of this function. So you can treat this like an exercise in integrating Dirac delta functions, but you can also think about it more physically. But that is all that is there in this equation. So this is what, if you are given an initial density, you will do to find the next and so on. So this is how you will evolve densities, the Perron-Frobenius operator. So for example, for this logistic map, which I have shown in this picture, we are starting from this density at time 0 as uniform density, and we are seeing how it is going to this invariant density. So at time 1, you apply this, and you can show that it is 1/2 square root of 1 minus x. That must be this red line here. And at time 2, it already has a shape, you see already that invariant measure has square root of x into 1 minus x. That is appearing already at time 2. So this thing is already appearing there as well. Here there is at x equal to 1, x equal to 0. And then there are interesting factors in the numerator. This is quite interesting. I don't see it anywhere, but actually you can work out that the most general at time n, what the density is exactly, and it turns out to be a very strange sum of square roots of 2's with coefficients which can be plus or minus 1. So, and there is a square root of 2 minus 1 minus x. And it leads to an interesting identity for 4 by pi, which I don't know whether it is known in the literature or not. So, but as far as we are concerned, we are just starting from an invariant, from a density which is not invariant, and pushing it to this, using this operator, rho p, Perron-Frobenius operator, and on these densities. So here is another, I thought, slightly amusing thing, but just very briefly, and we can actually make some connections to quantum if we come to it at all. By the way, irrational rotations, obviously, it's not going to equilibrate. I mean, we know that it has an invariant measure, but it's not going to go to the uniform. That's clear, because any rho of theta comma 0 goes to rho theta comma n, where this is just being rotated. Theta goes to theta minus 2 pi alpha n. So it's just rotated density. It's not going to the invariant uniform density. So such a system is said to be ergodic, but not mixing. So in fact, statistical mechanics really assumes both ergodicity and mixing if you wanted to reach an equilibrium. Okay. For the doubling map, 2x modulo 1, the Perron-Frobenius equation looks like this, because if you start from x by 2, you will come to x, because twice x by 2 is x. But also if you start from x plus 1 by 2, you will come to x, because x plus 1 by 2 into 2 is x plus 1. Modulo 1, you come to x. Okay, so both these numbers are between 0 and 1, and they are the pre-images of x. And this half is coming from this 2, that is this f prime. So now you can iterate this. You can say this is n. Now let's look at it at n minus 1, etc. And so if you iterate the Perron-Frobenius on any density, rho x comma 0, you will find this sum like this. Now if you stare at this sum, now this x by 2n is some number, as n is this time. If n is very large, x by 2n is almost 0. Plus k by 2 power n, this k is going from 0 to 2 power n minus 1. So this is actually going over all the points in the interval from 0 to 1. And this is just this summation of this. It looks like the Riemann integral, therefore, and it goes to the integral of the initial density over all position. So if we take our initial density to be normalized, which we will do so that its probability of finding the particle somewhere is 1, then you are proving by this that in the doubling map case, this is any density which can be Riemann integrable is tending towards 1, which is the uniform density. So coming to the question shown, you can have in this case densities which are invariant densities but which are not uniform. You can have infinite number of them. They will not be Riemann integrable like this. And actually there's a whole, I'll show you some very screwy functions, but even very simple ones, like for example, we know that 1/3, 2/3 is a period 2 orbit. So if you take delta functions which is concentrated on 1/2, 1/3 and 2/3, that's a measure which is on a periodic orbit. Obviously it's not going to go anywhere. It's just going to be, it's again invariant, but it's certainly not going to uniform measure. So any measure which is concentrated on periodic orbits is not going to go to the uniform measure. But these are all singular measures. They are not continuous with the Lebesgue measure. So if you take anything which is smooth, it will go to the uniform. Yeah, so this invariant measure mu is, it depends on the invariant measure. So there also Birkhoff theorem will hold, only that measure will be, it's a different measure. It will be the measure on this periodic orbit. Yeah. No, ergodic but not mixing. Like irrational rotation, Birkhoff theorem is valid. You will not reach that, but Birkhoff is not worried about that. Yeah, that you don't need mixing, because as time goes by, this orbit is going to go all over. The irrational orbit is going to cover the unit circle uniformly. So you don't need for that. In fact, we proved that. Eigenstate thermalization. Yeah. Supposed to, yeah. But again, it's very loosely used, the word ergodic. Yeah. Non-integrable. We'll just use the word non-integrable. I'll come to that. But here, as far as mixing is concerned, at this point, you should take it that any measure, any density will go towards the uniform measure, uniform density. Uniform or not uniform, sorry, invariant measure. But I'll come to a more precise definition of mixing. Okay, here is something cool. All right, so let's take this density here. Okay, it doesn't look like a nice smooth function, but it is actually. This nice smooth function is a product of the sine squares. Sine square pi 2 power j into x. J is 0 to n minus 1, where n is some integer. Here n is 8. Okay, you will agree with me that sine square is a nice function. Products of sine squares are nice functions. So this is a nice function, okay? And I put it through the this doubling map dynamics, and then what you see is this is time. This is n equal to 8. Actually, this is with time. Okay, ignore this is. So this is with time. It will. Yeah, this is n equals 8. This is. Now I'm starting with that. Now ignore this thing, but it's actually the same as n equal to 7. If I put this through the Baker's or this doubling map, it will smoothen it out to n equal to 7. And in the next step, it will smoothen it out to n equal to 6, n equal to 5, 4, 3. So this is just a product of 3 sine squares. This is just a product of 2 sine squares. This is just 1 sine square. And in the next time, constant, which is the invariant measure. So this is exactly like the, it's like the lowering operator in the harmonic oscillator quantum mechanics. So this is acting on this density and it's giving you this density at n minus 1. So it's a lowering operator this thing is doing. But you can see what its action is. The action is taking this rather non-smooth function and it's smoothing out into this density here. And this is doing it in finite time. It's not asymptotic. That's because I've taken this product of sine squared, and you can actually see that this is exact. It's not an approximation. And this product of sine squares is a very interesting function. It is coming as a Fourier transform, e to the power of 2 pi I x kx, tk, where this tk is a binary sequence. It's only plus or minus 1, and it's called the 2 Morse sequence. So it's a sequence of plus 1s and minus 1s, which are constructed like this. You start from 1, and you negate it. Let's say you multiply by minus 1, and you get minus 1. Now that is at generation, let's say 1. So you have these two. In the next generation, you take these two, multiply by minus 1, and you append it. So you take minus 1 will come from here, and 1 will come from here. You will have a length 4 sequence. Okay, and then you take this, negate it, and you append it, and you will get like this. So this is called the 2 Morse sequence, and it's got many fascinating properties. It's basically minus 1 to the power of the parity of the number tk is minus 1 to the power of the parity of k in the binary expansion. That is, you make binary expansion, count the number of ones you have in it. Minus 1 to the power of the number of ones is the 2 Morse sequence. I could go on for 1 hour about this, so I will not do that. But here you have a recursive relation. You can see the close connection. T2k is tk, 2k plus 1 is minus tk. And with this t0 is 1, t1 is minus 1, it will generate the 2 Morse sequence. So actually as n goes to infinity, this is an example of a multifractal measure. So these are actually already, you can see that they are not, although I said that they are smooth, and they are, but as n goes to infinity, it's a multifractal measure. For those of you who are, the sequence is this thing. So capital N, capital N is the generation. So 2 power n, so n is the, look, for example, here n is 8, right? I have taken n is 8, which means that there will be 2 to the power of 8 terms in the 2 Morse sequence, which are going into this. Actually, this is k is 0 to 2 power n. Yeah, that's correct. So the number, this is the generation, this n is the generation. So the number of terms in the 2 Morse sequence is 2 to the power of n. So here it's 256 and so on. X is just spatial coordinate, yeah. X is there. Yeah, you can think about it as a momentum, but here it doesn't have any such physical meaning. It's just a Fourier series of this. Yeah. Okay, so actually we found that the quantum, when you do the quantum, I'm not saying this just for this thing, it's fun, but on the other hand, actually it turns out that when you quantize the Baker's map and study this, which is closely related to these things, you will find such measures appearing as eigenfunctions and so on. And these are multifractal measures, so multifractal eigenstates and so on. They can be constructed as well as card states. In fact, if you look at where this peak is, where do you think these peaks are? Just from this is going from 0 to 1. So where do you think these peaks are? 1/3 and 2/3. And 1/3 and 2/3 are for the doubling map, period 2 orbit. So in fact, these things are periodic orbits come into these into play here, and these kind of, when you do the quantum, they will appear as scars of periodic orbits in these things. And it's also a fun thing, this product of sine square, for those of you who are worried that they can actually do this in closed form, you can do cos square, but not sine square. Okay, so you can challenge yourself to do the cos square of this, cos square pi 2 power jx, okay, and then product of this. All right. What? Huh? Yeah. Yeah. Well, boundary of x is from 0 to 1. K is all possible values from 0 to 2 power n. If you want, you can, divide by n and make it a discrete Fourier transform, because after all, this is only a discrete thing. But this x for me here, because I'm describing this, x is also continuous for me. Okay, so yeah, here is some facts. So Perron-Frobenius is a non-expanding Markov operator. It takes densities to densities. Okay, and it's non-expanding. If you take some norm of the function, it will be smaller than this. It's kind of contracting. So the eigenvalues of P give mixing rates, which we will come to. It's also called the Polycott-Rouel mixing rates. And for the doubling map, 2x modulo 1, we can ask for the eigenfunctions of these Perron-Frobenius operators, not just the stationary states, but eigenfunctions. So in fact, these are like the non-stationary states of open systems. So it's a big and very confusing literature, and it's actually quite mathematical, but very interesting that the so-called Bernoulli polynomials are in fact eigenfunctions of the Perron-Frobenius for the doubling map with eigenvalues which is 1 by 2 power n, where n is going from 0 to infinity. And therefore, these resonances are just 1 by 2 power k for this map, where k is 1, 2, etc. And Bernoulli polynomials are defined by the generating function of this. They are very fascinating objects, and they're just polynomials as far as we are concerned here. So B0 is the uniform density, but everything else has negative parts, so it's not a density. So they will, so it's not that this is positive and it will go to positive alone. This is actually decaying to 0. And these also support very exotic, nowhere differentiable, everywhere continuous Weierstrass function type eigenfunctions for the doubling map. So this very simple map for which we can solve things analytically, these operators which are telling how densities are evolving are already very complex objects with very interesting eigenfunction structures and so on. So there are these functions which are everywhere continuous, nowhere differentiable. You can see kind of again some kind of fractal objects like these show up in these. Yeah. Yeah. Correct. Yeah. So yeah, so it's a bit like these. Yeah. So if you take a positive function like a density, right, then acting on a density gives you densities. So that's what it will. So a Markov operator will do that. It will give you your starting from some probability distribution. It will give you a probability distribution. Yeah, you can not here in this context. It's something you can think about it like a Markov process or a Markov matrix. When you act on with a stochastic vector, it will remain a stochastic vector. It's going to take probabilities to probabilities. So you can think about it as a constant thing. But if you start with something not a probability, it will not necessarily be a probability. And it is contracting in this sense that it is less than or equal to the norm of this vector which you're starting out with. It's contracting. Distance of what with the invariant density? Yeah. 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 I mean, distance to the invariant density will be decreasing monotonically. Yeah. Yeah. And in fact, those rates are given precisely by these. Yeah. Uh, huh? Yeah. So actually, I seem to have some chaos in this. Since you guys are asking me, maybe I will go there and define mixing. I thought I'll show you some more examples, but here is mixing. Okay. Also, since I should have finished my classical at least by now. What is mixing? So we start with, so this is a book by Arnold and Abbes. Okay, that is hiding here. Ergodic Problems of Classical Mechanics. It's a very nice book. So they recommend that you take M to be a shaker full of an incompressible fluid, which consists of 20% rum, that is this one, and 80% Coca-Cola. Okay, that time relations between Russia and US was okay, I think. 8.1. I don't know if there's something else you have in mind, but that's the common usage. Yeah. So if A is the region originally occupied by the rum, then for any part B of the shaker, the percentage of rum in B after M repetitions of the act of stirring is this. That is, you're doing this like this, so the rum goes around like this. You're asking how much of the rum is in this region B. So the action of A, there is some dynamics of phi and A after time n. How much it is intersecting with B? How much is actually this measure? Again, I told this invariant measure. So that is the natural measure in all of these things. So this is the measure of this. How much volume is there in this? This is the fraction of, this is the actual volume of rum that you began with. So this is a fraction of rum in B after time n. In such a situation, physicists expect that after the liquid has been stirred sufficiently often and going to infinity, every part of B in the shaker will contain approximately 20% rum. Okay, so this leads to the following definition, that the measure of, here I've used F instead of phi and minus n instead of n. F to the minus n A intersect B tends towards this measure of A into measure of B. You can divide by measure of A, you get this. And I've assumed that the measure of the whole thing is 1. The phase space is 1. So basically, this is the definition of mixing. Okay, as n goes to infinity, this has to be true for almost every open sets A and B. Then you call F to be mixing. So that is actually our natural tendency of mixing. What is when we put sugar and mix, or rum and mix, whatever it is, we expect that the rum to be uniformly put in here. Now, if it was ergodic, what will happen is this A can just move around everywhere, but it will not mix, but it can still move around everywhere. That is ergodic, but not mixing. Mixing is when it's actually doing this. Okay, so I'll probably very quickly, I've come to the, I've now finished with the more simpler, I mean, not the simpler, but I used the 1D maps to actually motivate a lot of concepts which are generalized to any dimension, and introduce the basic concepts of or ingredients and definitions of chaos, which are valid in general, not just in that particular context. Because as we are going into higher dimensions, it's not so easy for us to work out all the periodic orbits, show that it is dense, and show that something is sensitively dependent, or even to show that something is ergodic, let alone mixing. Okay, so here is our two oscillators. One which is, I'm going back to Hamiltonian systems, which are more respectable for a physicist. So, but it's now 1 degree of freedom, not even 2. Okay, some kinetic energy kind of part, potential energy kind of part, but now it is dependent on time. So there is some periodic forcing, let us say. Okay, G of t is t plus t. For example, let's take a harmonic oscillator parametrically forced like this. So epsilon is 0, is this the usual harmonic oscillator. Epsilon is not 0, this is a forced harmonic oscillator. Now let's consider a pendulum which is nonlinear, which is very close to this. So I'm just replacing this q square by 2 by 1 minus cos q. So for small q, it is going as q square by 2. So it's a forced pendulum and a forced harmonic oscillator. Equations of motion are exactly from Hamilton's equations. They are given by this. One is linear time-dependent coefficients, non-linear time-dependent coefficients. Now, if you were to plot Q versus P, the phase space of the harmonic oscillator, forced harmonic oscillator, you will find this picture. Okay, this is one orbit. Obviously, they are crossing with each other because there is time dependence. Okay, so the orbits can cross because of this time dependence. The field is not constant. The vector field itself is non-autonomous. And this is another initial condition which is very close by. I've written the initial conditions, and the difference between the momentum is 0. Here it's 10 power minus 3 in this. And you will agree that there's no essential difference between these two. This is for the pendulum for the same initial conditions. Okay, and you can see that that is quite different from these two. So this is again the sensitive dependence which I pointed out. So nonlinear systems like this can show chaos, and linear systems like this no chaos. Again, to analyze such things, these pictures are not good to analyze. Just as we did Poincaré surface of section, we will do a stroboscopic map here. Sometimes people call this also Poincaré section, where we are looking at the orbits Q and P for every period of the forcing T. Okay, so we have some base time, let's say T0. So we take some position and momentum at that T0. We evaluate for a period T, and so that is this evolution is given by this F to Ft. T0 is a base period. This is equal to the position at T0 plus T, momentum at T0 plus T. Because we have taken this time period to be, this evolution to be the period T, the system's Hamiltonian is coming back to its initial state because it's periodic in that, and therefore this is true, that we can compound this map by itself, and you will get the map for a time 2t. So it's abelian structure. If you don't integrate it for period t, this is no longer the case. So it's important that you evaluate it for period t. Then you get an abelian structure, and therefore you can define a map like this called the stroboscopic map, which is given by integrating for a time t. And then you get a discrete map. Now these things are related by a period t. Okay. And this is again an area preserving map if you are started with a Hamiltonian system. So now these complicated looking pictures here, they simplify and you get ellipses. But now they are maps and you get ellipses. If you take different initial conditions, you'll get concentric ellipses for the harmonic oscillator. So these are not simple harmonic oscillators, they are forced parametric oscillators. The stroboscopic map are ellipses, whereas the same energy, the same initial conditions, this is the harmonic, this is the one orbit, this kind of orbit for the, just 1 minute. So this is for the forced pendulum, and this is for many initial conditions, the forced pendulum, and you can see that there is again this kind of mess which we will call chaos, and this ergodic orbit here, and these resonances which are not chaotic. Yeah. What is going on is, let's take one of these points. Yeah, I'm sorry about that. So the axis is Q and P. Okay, position and momentum. No, it should have been there. Position and momentum. Okay, so that is the phase space, Q and P. And what we are doing is, let's say that you take some initial condition here. Okay, that is up to you. So I've taken, let's say, 0 Q, and momentum is something here, -7. And then I will integrate this using these equations, and I will integrate it for a time t, capital T, which for me here is 1, because that is the period. So I will integrate it for 1 second, and then I will plot the next point. And then I will integrate for another 1 second, I will get some other point, another point. So this is all a collection of points which are separated by 1 second. I'm not drawing them continuously. If I draw continuously, you will find that it will be like this. So that thing is lying somewhere here, the ellipse is lying somewhere here, where they are all separated by 1 second. And this one is different initial conditions. This is started from one initial condition, many initial conditions. And this is for the harmonic oscillator, this is for the pendulum. Yeah. Yeah. Separation by more than 1 second or? No. You see, if it is 2 seconds or a multiple of a second, it is still okay. But if it is anything else, it will not make sense in the sense that this condition is no longer true. That is, if suppose this is some t prime where it is not a period, suppose you integrate it for half a second, and then if you wait for, I mean, if you iterate that map another half a second, it is not the same as iterating this for 1 second. Okay, let me be. This is the definition of the stroboscopic map. What we want some map which you can iterate. So you should do integration for some time, and then keep doing that, and then you have found some map. Okay, you want to now iterate that map, and that should give you the dynamics for the long time. If you don't do it over a period, but a shorter time, that iteration of that will not be related to the original dynamical system. Why? Because when you iterate that for a shorter time, your initial, the Hamiltonian vector field is different at that time. The vector field depends on time. So this is a period with period 1. So you have to wait till that time before this vector field is come back to itself. If you do twice, then you will be losing some point in between, that's all. You will be getting half of these points. Yeah, because that will be a subset of this, right? Yeah, it will be still an ellipse. But if you choose something which is not commensurate with it, or see, suppose you integrate every half second and put a point, which is still okay. Okay, you will get some real dynamics, and that's not the same as iterating what I am saying here. But you will start getting a more complex picture. You will be getting, here for example, I'm looking at it after very short time intervals after all. Okay, good. So why are we getting ellipses here despite these kind of complicated functions? In fact, for a linear system, whatever this function g is, this map which is written here for the harmonic oscillator is a linear map like this. And because it's a harmonic oscillator, it also has determinant 1 condition. So if it's a stable system, it will always form an ellipse. If it's stable, it will always form an ellipse. If it's unstable, it will go off to an hyperbola. Okay, so this is coming from basic Fouquet theory, but you can try to reason it out. So, okay. So now we are interested actually in these kind of nonlinear maps. So we got such pictures from 2D flows like quartic oscillators, coupled quartic oscillators, when we did Poincaré surface of section. Yeah, so they are all connected in the sense that they are all two-dimensional area preserving maps. So the mathematical object which is underlying these things are two-dimensional area preserving maps. And so we will study two-dimensional area preserving maps. Yeah, so that's what I'm coming here. So let's now forget about everything and say that we have a position and momentum at discrete time n, and we are finding position and momentum at discrete time n plus 1, okay, through this map which is specified by two functions f1 and f2, okay. And now given f1 and f2, you can put it, this is iterating, it's even simpler than differential equation solving, and you can find out what these orbits are. So these can come from stroboscopic maps like what I said here before, or they can come from Poincaré surface of section. And what we will consider are generally area preserving maps, which means that the determinant of the Jacobian of this transformation is 1. Okay, so this is a transformation. In fact, it has to be a canonical transformation if we are thinking about this as position, momentum, etc. And the determinant 1 of the, I mean, we calculate the Jacobian, which is given by this derivative of f1 with q1, f1 with pn, f2 with qn, and f2 with qn. This is the Jacobian matrix. So this is playing the role of the derivative of the map at Q and Pn. Okay, and that has to have determinant 1. It means that you have a map of the plane into itself, let's say, you take any area in that area will change. Area will change meaning that region will change, but that area of that region will not change. This is like the Liouville theorem of classical mechanics, but actually, as I said, the origin of this is not the Liouville theorem, but it's very closely connected. Yeah, so, but in a 2D flow, for example, 2D flow, Hamiltonian flow, so 1 degree of freedom, it's the Liouville theorem, because there the volume is the area. But here they are higher dimensional, so actually it comes from what are called Poincaré-Cartan invariants. So these are coming from the Poincaré-Cartan invariants, which are, so actually there are these, the Liouville theorem is only one of n integral invariants. And so this is coming from the other integral invariant, which is, probably I won't go into that, but it's coming from Poincaré-Cartan invariants. What about them? No, there's no such, I'm not imposing any restrictions on that. They are area preserving maps, that's it. Okay, but for KAM theorem, for example, to hold, then you would have to have very smooth functions. If these are not smooth functions, KAM theorem may not hold, and so on. Okay. No, nothing. Here I'm not linearizing anything. You can linearize, but I'm just calculating derivative. The linear map will be specified by the Jacobian. But I'm not linearizing or anything like that, no approximation. One is simply because how do areas transform? You have some transformation. Areas will be transforming as the determinant of the Jacobian of the transformation, very general mathematics principle, and not just in 2D, any dimension. Yeah. Exactly. Yes. They are ordered by different times, that's all. They are in the same phase space. See, even in normal, in usual thing, right? Time evolution is a canonical transformation. Yeah, so this is time evolution. Better be canonical. Okay. Yeah. So in higher dimensional maps, you can generalize this to higher dimensions. 4-dimensional map, let's say. In that case, it's not only that the determinant of the Jacobian has to be 1, it has to satisfy the symplectic condition. It has to be a symplectic matrix because it has to be a canonical transformation. Every symplectic transformation determinant is 1, proper symplectic transform. Okay. So in this case, that condition, there's no other condition except because it's just 2 by 2 case. All right, good. So just as last time, when we take a trajectory, let's say initial point Q0 P0, and we find some delta Q0 around it and delta P0, some small difference in that, then that difference is getting multiplied by this Jacobian. Just as last time we saw how the modulus of the derivative was giving you the expansion factor. Here the derivative role is played by the Jacobian matrix. So this is precisely, as you said, linearization if you wish. Okay, you're doing linearization of this, and that is giving you delta Q1, delta P1. And then further time. So now you multiply by the Jacobian at each of these points, and they need not be the same. And that will give you the difference at time n by this product of Jacobians along this orbit. So there's a central orbit, Q0 to Qn minus 1, etc. And how this, so that's a tangent map. So this product of the Jacobians you can write as one matrix, one product of 2 by 2 matrices. And then you can ask, how is the norm of this vector related to the norm of that initial vector? As you can see, we are going towards Lyapunov exponents, definitions of that. So the eigenvalues of the product of the Jacobians will matter. So actually, if you take the norm of this, you will see that you get Jn transpose Jn, which is a positive matrix. There's nothing about positivity or not for the Jacobian, but this is a positive matrix. If its eigenvalues will be positive, and if the eigenvalues square are the spectrum or the eigenvalues of this, then that will depend on the time n which you have gone on this. The exponential rate at which these eigenvalues are growing is defined as a Lyapunov exponent of this point q0 p0. So in other words, you see how these eigenvalues of the this or the singular values of this matrix Jn is growing in time. If it's exponential, that rate is the Lyapunov exponent of this. And now you can see that here there will be, it's a 2 by 2 matrix, you'll have 2 eigenvalues, and therefore you'll have 2 Lyapunov exponents for this. In general, for a n-dimensional map, you will have n possible things, and this is called the entire spectrum of Lyapunov exponents. Yeah. Where is that? Oh, okay, yeah. Sorry. Yeah, there is a Pn there. Thank you. Sigma I square are the eigenvalues of this Jn transpose Jn. Yeah, sigma is just square root because this is just a positive matrix. So in other words, if you find this, how you find singular values of this, you will find the single values of this by finding the eigenvalues of this. But by the way, I mean, I'm going through this, and this is actually the definition of Lyapunov exponent, and it's a proper definition, but it's also simpler to just find out eigenvalues of Jn itself, but Jn or the Jacobian eigenvalues need not be even real. They can be complex because there's no thing to that, there's no structure to that. But each of the, if you take the modulus of those, they will also be growing as the largest Lyapunov exponent. So there are connections between the eigenvalues of the Jacobian and the singular values, but I don't want to get into those aspects. So basically, it's telling you how you can find the Lyapunov exponents of these things is by taking products of the Jacobians and finding out the eigenvalues, how they are growing of the Jacobian, or finding out the singular values and see how they are growing. Okay, now let's come to this kind of forced systems give rise to these kind of maps, stroboscopic maps. Still, it is difficult for me to derive it. For example, if you give this system here and ask me to derive the map, I can't do it because I need to integrate intermediate times. You can try hard, I mean, you can do some elliptic functions and so on, but actually it can be quite messy. So one of the very popular things is to take just impulsive kicks. So there's a train of impulsive kicks which is being applied at this time interval t. So there is now periodic kicks of this period t, so it's still periodic, and this is some function of momentum, maybe this is some function of positions. So these are called kick systems. Then you can write these differential equations from Hamilton's equations, quite so. I'm denoting by this delta capital T, this train of delta functions, okay? So now, what exactly is happening? So now, let us derive now the stroboscopic map for this, okay? So what is the stroboscopic map? We said it's going to relate position and momentum across one time period. Any time period, that base time can be anything. So let's take the base time to be just after kick n, that is after time n into time t, n into t, just after that, to just after the kick n plus 1. So what happens between these kicks n plus to n plus 1 minus, there is nothing here. It's just evolving by this free particle motion f of p. Between the kicks there is nothing. So it's free particle. So the momentum at time n plus 1 just before the time n plus 1 is just the momentum after time n. And the position just before is given by this because this Pn is constant. momentum is constant, so I can just integrate this out. Okay, very simple. It does not matter what this function is. It can be p squared by 2, it can be cos p, whatever it is a derivative of this evaluated here. Now we come to the interesting part of the kick. From the kick, across the kick n plus 1, just before and just after, this position is frozen because the momentum is not taking all kinds of values, it's just being, there is a kick across a time which momentum can change discontinuously, but if you integrate this across an infinitesimal time period, this is going to go to 0. Across an infinitesimal time, it's going to go to 0. And therefore the position is frozen. So Qn plus 1 plus is equal to Qn plus 1 minus. In the previous one, momentum was frozen. Here position is frozen. And momentum is changed abruptly because of the impulsive motion. So the momentum after the n plus 1th kick is the momentum just before the n plus 1th kick. Actually, this is also a mistake here. This is Pn plus 1 minus, okay, this is Pn plus 1 minus the integral, minus the derivative. You just integrate this because this is now a constant Vq, you're just integrating the delta function which gives you t because of this t down here. So you see the connection, you see the kick and the free part is kind of interchanging momentum and position. Now you put them together because you want to relate n plus 1 plus and Pn plus 1 plus to n plus and q plus. So you do that and you get this map that the position after the n plus 1th kick immediately is given by this Qn plus t, the derivative of this free part, and the momentum part is given like this. Okay, so it's a kind of discretization of the continuous equations of motion of a 1D particle with this time t. So now there is an explicit two-dimensional map. You can verify explicitly, and please note that here there is Qn plus 1. It's not Qn. If it was Qn, it will not be area preserving. The fact that it is Qn plus 1 is essential. It's some kind of Euler discretization. So there is a vast family of maps which people have studied. So one of the most popular ones is when there is p square by 2, v of q is cosine. So it's a kicked pendulum or a kicked rotor. Okay, so that's called the standard map. Variously, it's called Taylor-Cherenkov map. It's called the kicked rotor. So it's just given by this function, and this is the map, 2D area preserving map. Now we're thinking of this q as an angle. So you can put a modulo 1 condition there, cos 2 pi q, and the momentum is given like this. Okay, so there is this factor g, which is the kicking strength, and this time period t, I have written one parameter map in which I have redefined some of these variables. I've scaled the momentum, and this k is the time period square times the kicking strength. So this is a one parameter family of maps. This one parameter family of maps has a symmetry, an important symmetry, where you can translate by momentum by 1, and that commutes with the dynamics. So it's some kind of crystal symmetry along the momentum. So if you have this symmetry QP going to QP plus 1, it commutes with the map M, if you call this map M. So the consequence of that is that, so I have plotted here this map for many initial conditions. So there's Q and P, you're not seeing the Q. And this is for K is 1. K is 1, here I have put the same map with a modulo 2 condition along momentum, a modulo 1 condition along momentum. What you will see is there are 2 copies of this map on this. So there is that symmetry of this. So which means that this map here can be studied with a modulo 1 condition also in the momentum because of this. So this can be studied as a map of a torus into itself, and that is, so this can be studied as a map of a cylinder onto itself or as a torus onto itself. So here I'm plotting many orbits of this map as a function of the single parameter. When k is 0, this momentum is a constant, it's just a rotor. There is no forcing, and this is an integrable system. because momentum is a constant. And therefore, this is just straight lines here, but so every orbit will be a bunch of lines here with this constant momentum. Okay, sorry? Yeah, K means K equal to 0, G is equal to 0. Yeah, and when K is 0.5, you see this complex enough diagram where you see these stable orbits. Here at the origin, this origin is turned to be a stable orbit. You have to know, put a torus boundary condition. You have to identify this side with this side and this side with this side. You have a stable periodic orbit at the origin. You have an unstable periodic orbit here. Okay, that looks like a pendulum. But you have much more structure. You have like this resonance at period 2 stable point and a period 2 unstable point, period 3, and then you have these tori like these. And this is K equal to 1. These tori are getting broken, and you can see more sort of chaos developing around these unstable points. K equal to 2, the stable point at the origin is still stable, but a lot of things are lost in between. There's a lot of chaos here, and the stable period 2 orbit remains. K equal to 4 is a critical point where this orbit here actually loses stability, the fixed point at the origin. Yeah. Orbit. So each color is a different orbit, initial condition. You take one initial condition, iterate it 1,000 times. And at 4.5, this origin is turned unstable. So there's undergone a bifurcation, and you have some new periodic points maybe born there, stable regions. But essentially here, for example, the Biendu, fact that there's only blue implies that I've put only one orbit here. So this one orbit is going all over like this. It's ergodic, at least it's ergodic. It's actually also mixing. K equal to 6, you see that there are these two small islands fighting this war against this entire chaos. This is just one orbit. That orbit does not penetrate this. K equal to 9, it looks like there are no periodic or stable regions at all. One orbit seems to go throughout this square. At 9.26, which is larger than 9, you start again to see small orbits. So it's not as if you keep increasing K monotonically, you will not see islands. It's a more complicated behavior than this. Origin, yeah. So there is another critical point, which is a well-known point, which is 0.9, approximately K is 1. At that point, this kind of tori which are connecting this, they break. So this is K is 1. So just before this, actually it breaks a rotational torus, and it leads to a diffusion in momentum. So something here can go across like this. So if you put it on a cylinder, the momentum here, you see, there's no gap here. So things can actually, momentum can increase like this, and momentum can diffusively, can grow indefinitely. And in fact, it grows in a diffusive manner in this case, like a Brownian particle. The momentum undergoes diffusive growth. Okay, so yeah. It's coming because this map, this angle is by kind of construction modulo 1. It's an angle. So it's naturally a cylinder. It's like a kick pendulum. Pendulum is a cylindrical phase space. Momentum is not naturally its angular momentum, so it need not be periodic. But what I'm saying is this thing here has a periodicity of 1 is a symmetry. So if you don't do this modulo 1 in momentum, you will get copies of this. If you do modulo 1, you'll just get copies of this everywhere. So if you put modulo 1, it's still a smooth condition, which is not, it's not violating something. But if you put modulo half, for example, that will not be, it will be a different dynamical system. You should not put modulo half, but you can put modulo any integer, then it actually commutes with this map. So it's a symmetry. This translation is a symmetry. It's like, what is that? It's just like crystal symmetry. You can It's like some Brillouin zone or something. You can look at one principal Brillouin zone and then there is not translation in time. This is translation momentum. Ah, yeah, of course, there is that time symmetry is there. It's periodic. Yeah, it's periodic. Otherwise, we can't construct a stroboscopic map. No, no, no. This is not coming from that. This is coming because of the p-square dependence in this. So it becomes linear in momentum. But for example, if it was some weird, I mean, if it is cos p, cos q, no problem. It's already, in fact, there's an important Harper map which is coming like that. But if it was p cube or p power 4 or something like that, then it's not, then you'll get some p square here, then it's not obvious that there is that symmetry. So you can cook up a lot of maps. You can cook up a F and V and have your own map. You can name it after yourself. Yeah, 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 you can. Yeah, they will be. As long as you have derivatives. As long as you have derivatives, the but it's important that it's qn plus 1. Arbitrary. Name it after your cat. Yeah. Okay, I think I have kept my promise of not going into quantum today also. Yeah. Yes. Yeah. 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 That's a linear map. It leads to a linear map and it will lead, because that's exactly the harmonic oscillator type which I showed, right? It will be like this. It will lead to a linear map that can be stable or unstable, but no chaos. A good question. For me, at least in this context, right? These are the simplest system which can display these chaotic behavior, complex behavior. So in fact, these were the first systems that were studied from the point of view of chaos in physics. So 1 degree of freedom leads to two-dimensional phase space. We said thanks to Poincaré and Bendixson, you can't have chaos. You can have only that. So you need to step out of 2 degrees of freedom, two-dimensional phase space. You can step into 4-dimensional phase space and then reduce it by energy to 3-dimensional flow and so on, Poincaré surface of section. Still, there is this possibility that you can go to 3 dimensions by going to time as your other dimension. So now some people call this 1.5 degrees of freedom because there is a 3-dimensional phase space where that other time direction is your other phase space direction. So it's the simplest systems which can display chaos. And you can derive some, for example, the Poincaré surface of section for chaotic sections and you can't derive even for this anharmonic oscillator and so on. You have to rely on numerics. You cannot derive analytically some interesting Poincaré surface of section which is chaotic, but you can if within it. But of course, physically, time-dependent problems have taken over. There's a huge amount of Floquet literature, a lot of experiments. This particular thing itself, standard map, quantum experiments have been done since 95. So pulsed lasers are common. So that gives you this kicks periodic in time. So in fact, even this uh, periodic in time is fine, but having this delta kicks is quite an extreme thing because you are inputting a lot of energy into this when you're doing this. Whereas if it's a more smooth thing like cosine, sine of t or something like that, then it's a different thing. But again, I can't derive the surface of section or the stroboscopic map analytically. Yeah, those are the pulsed lasers. They just come on and off. Yeah. The cosine actually is in time, is in space when they are doing that. And so that's essential for the for this uh, for this potential, like this cosine here, that is created by standing waves, and then there are pulsing, there are these lasers are pulsed between these things. Yeah. The map doesn't depend. The map is a map of the torus into itself. There are many orbits, so the orbit will depend on the initial condition. There are infinity of orbits. Okay. Yeah. So actually, this I talked about the KAM theorem. That can be seen in action here. So these are actually what you are seeing are irrational tori. These are tori corresponding to irrational momentum p. They are irrational. You take a point, it will just cover this irrationally, and they survive this perturbation. Here, this is p equal to 0 is certainly not an irrational number. That is broken up by Poincaré-Birkhoff theorem, and it is replaced by a stable orbit and an unstable orbit. And here at p equal to half, that is also, of course, not an irrational number. It is Poincaré-Birkhoff theorem. It's replaced by two stable orbits, this, and two unstable orbits. And there will be a 1/3 which is broken up into three stable orbits and unstable orbits, and so on. And then there will be a golden mean here, square root of 5 minus 1 by 2, that will survive the longest. And then when that is broken at around k equal to 1, all the KM tori are broken, and then large scale chaos develops. So there is quite an involved story there. Yeah, I think I should stop it well above time. Thank you. So next week is h bar not 0. I don't know if on YouTube they have. Yeah. Dense set of periodic orbits. As I said, actually it's been proved that the first two implies the third. So yeah, so it's sufficient for you to have periodic orbits dense set as well as this. But actually for practical purposes, if you have sensitive dependence on initial, people keep calculating only Lyapunov exponents. Sensitive dependence on initial conditions, and it is bounded, then you can be assured that that's chaotic, and for all practical purposes, this is true. Yeah, so it won't be obvious, but in a situation like this, there is a dense set of periodic orbits somewhere there. There's just one orbit which is going around, but you can find periodic orbits. Of course, here the origin are unstable period fixed points. This is also an unstable fixed point, etc. So they'll all be unstable, but there are orbits, periodic orbits in there. Oh, good question. He's asking if there is some f of p and v of q, which is so that it's chaotic. You can also turn your question on the head and ask, what f and v do not give you chaos? Integrable maps. And in fact, I didn't display that, but there are some examples of nonlinear maps. Of course, q square by 2 is linear, so that's trivial. It's integrable. But there are nonlinear maps which are integrable. Very few. There is no general prescription for constructing integrable systems, and therefore no general construction for non-integrable systems. In fact, this is true not just for maps, for any Hamiltonian system. Somebody gives you and says, okay, you know what is, you can define integrability, but can you tell me if this Hamiltonian is integrable or not? There's no algorithm which will, if somebody finds as many constants, well and good. So unfortunately, there's no constructive algorithm to do that. Yeah. Yeah. Um, so periodic orbits, I mean, the Lyapunov exponent, onset of chaos means it's actually measuring kind of divergence of trajectories. Yeah. There are two entropies which are important. One is topological, other is Kolmogorov-Sinai. I haven't even come to the other one. But the Kolmogorov-Sinai is more like mixing. Topological, as I told you, is related to the how the periodic orbits are growing, and the fact that it's topological means that it doesn't depend on the metric and so on. It's just a question of the exponential rate of growth of periodic orbits. I don't know if there is some other kind of interpretation to it. I actually don't know. Yeah, yeah. My favorite ones. Yeah. No, not according to general. Hmm. See, you look at our definition of integrable systems, right? We said that there are these tori. You have these constants of motion, first of all. You have these n constants of motion. And because of that, they lie on this tori. And what is the motion on the tori? Motion on the tori is action angle variables. So this theta is just evolving quasi-periodically. So theta is just winding on this torus. And the maximum, it can either be periodic if the frequency is rational, or it's commensurate in some higher dimensions, it's periodic, or it is quasi-periodic. So that's also in the maximum that can occur is this for k equal to 0. So let me, so this is some function of I. So 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 this is some I, or this is some omega, which is some function of I. Okay. Yeah, so it's just this kind of mm, so let's actually probably solve one of these things. I don't know. Qn, let's solve actually the standard map itself. So Qn plus 1 is Qn plus Pn. In this trivial case, so Pn plus 1 is Pn. It's exactly like that rotation map, right? So so this thing is just a constant. So this Qn is just Q0 plus n times P0. So there can't be any sensitive dependence on initial conditions. So you can take delta Qn to be some delta Q0 plus n delta P0. Delta Pn is delta P0. Okay, so at most what can happen? Delta Q0 delta P0 some n1 0 1. Right. So that is your so it can only change polynomially in time. The delta Qn can grow only polynomially in time, and therefore the Lyapunov exponents will be 0. There's no sensitive dependence on initial condition. It's just quasi-periodic evolution. So no integrable system can be chaotic. So it won't, first of all, it won't have this dense set of periodic orbits on that. It won't be sensitively dependent on initial conditions. At most, it can be ergodic. Even a 1D harmonic oscillator is ergodic on the energy thing. It's just visiting every point of the energy shell. So ergodicity is in some sense trivial. Okay, I think we should stop. Thank you.